Blue stars are known to be the youngest in the galaxy. Because they are only a few million years old, they are still clustered together near the clouds of dust and gas from which they were born. Photographs show that as these clouds become smaller, they become darker, which suggests that they are collapsing to form still other stars. No one has actually witnessed stellar birth, but theoreticians do have an idea of how it probably occurs. In theory, when a cloud of gas and dust reaches a certain density, it could collapse or fall together under its own weight. It might fall into one or more separate units, forming single or multiple star systems, perhaps with planets. The volume shrinks a billion times. The cloud becomes hotter and denser as it continues to fall in toward itself. At the center of the sufficiently massive cloud, the density and temperature might be so high that there are collisions between the atoms of hydrogen, and some of these collisions are energetic enough to produce nuclear reactions. The release of energy creates a gas pressure that stops the collapse of the cloud. Some clouds are unstable and move in and out or pulsate as the forces of gas pressure and gravity seek to adjust themselves. Eventually, after millions of years, as the hydrogen burns in the furnace of the interior, a stable cloud of gas, a stable star, one of nature's most magnificent inventions, is born.
All the evidence we have on star formation indicates that one star isn't formed by itself, but rather that they form in big bunches all at once, what we call star clusters. These clusters can number anywhere from a few dozen stars up to many hundreds. We know this is true because we see stars being formed right before our eyes at the present time. For example, here in this picture of the Orion Nebula, we see the cloud of gases, that's the green stuff. And you see the stars, 4 bright ones there in the middle and a bunch of little fainter ones around the outside. Now the stars in there which are going to end up like our sun are not those big bright ones. Those are a special class of heavyweight stars. But it's one of those faint ones out there which might possibly be a future sun with planets.
Within the Orion Nebula, astronomers can see dark areas of cool gas which they believe are condensing into stars. These clouds of gas are basically composed of 90% hydrogen and 10% helium, with only a trace of heavier elements and dust grains.
One of the things that you always have to keep in mind when thinking about the formation of a star is that there's going to be a certain amount of rotation. You start with a big diffuse cloud of gases, and we're now talking about a subsection of what was once the big interstellar cloud, just a little piece of it that's going to make one star, or possibly a double star. Anyway, there's a certain amount of rotation, and as the cloud contracts down more and more to form a star, the rotation is going to speed up. If there's enough rotation there, the thing may split before getting down to the size of a star, and you end up with a fairly close double star, for example. In the case of the sun, it's thought that there wasn't that much rotation, and it contracted down to something like the, well, not right down to the size of the sun today, but down to something like the orbit of Mercury with a radius of a few million miles. And at that point, the sun was spinning pretty fast, and maybe some stuff spun off from the equator, or maybe there was just some stuff that didn't quite fall in and was circulating there around the equator of the sun, and that material formed the planets eventually. And it would seem most likely to be a question of just how much rotation is present. A lot of rotation, you'll get a double star. Not so much, you're likely to get a single star with planets. If there's very little rotation, you might get a single star with no planets.
The exact effect of angular momentum on stellar and planetary formation is far from understood. There are still many mysteries to be explained, which may be accomplished with new observational techniques. Astronomers believe this cosmic cloud of gas and dust to be a maternity ward of stars. Here, Condensations are forming and the force of gravity is attracting more particles. For several million years, the nucleus of each star will continue to become hotter as the star contracts. As these young stars evolve towards the main sequence phase of their lives, they are first detectable by their emission of large quantities of infrared radiation.
We've only recently learned to detect and analyze the infrared radiation that comes to us from the stars, but it is of unquestionable importance to us because it helps us understand the formation of stars. Now, the formation of a star is more than simply a progression from a large, thin cloud of gas to a much smaller and denser star. It's also a progression of an environment from a few degrees above absolute zero in temperature to something that's thousands of degrees Kelvin at the surface. And until the star gets that hot, that is when it's cooler, it gives off most of its light in the infrared. Well, the same would be true with any object that's only a few hundreds of degrees in temperature. Now, even after the star reaches a higher temperature and gives off visible light, it's still surrounded by dust. And this dust is left over from the cloud from which the star originally condensed. Well, until that dust is blown away, it absorbs visible light from the star and re-radiates it at infrared. So that's two reasons, then, that we must look into the infrared to see what's going on. And finally, at the cool temperatures that are typical of the formation of a star, the gas is in molecular form rather than in atoms, and most of the spectra of molecules are consisting of radio